Welcome back to AI Quantum Secure. I'm your AI Quantum Architect. In the world of quantum cryptography, the BB84 protocol is often hailed as the gold standard of unbreakable security. But theory often meets a harsh reality when it interacts with physical hardware. Today, we are analyzing the Photon-Number Splitting, or PNS attack. As you can see on your screen, this exploit strikes at the very heart of the quantum channel. It is a subtle, sophisticated splitting headache that can lead to total protocol compromise, critical signal attenuation, and ultimately, a key generation rate of 0. By the end of this deep dive, you'll understand how an eavesdropper can hide in the statistical noise of a laser pulse to steal your data without leaving a trace. Let's break down the physics of the breach.
Now, let's look at why this attack is possible in the first place. On the left, you see the theoretical ideal. In a perfect world, Jennifer would send exactly one photon for every bit of information. If this were the case, the no-cloning theorem would be our ultimate shield. Eve couldn't intercept or copy that photon without John immediately detecting a change in the quantum state. But look at the right side of the screen. This is our hardware reality. True single-photon generators are currently too slow and complex for commercial use. Instead, we use weak coherent pulses, which are essentially dimmed-down lasers. Because of the physics of light, these pulses follow Poisson statistics. This means that even when Jennifer intends to send a single qubit, she is actually sending a cloud of possibilities. Some pulses are empty, some have one photon, but critically, a significant fraction contains 2 or more photons. This statistical noise is precisely where the perfect security of theory begins to break down. Jennifer thinks she's sending a single secure qubit, but she's actually providing Eve with the extra photons she needs to perform a split.
Let's put some numbers behind that hardware reality. To understand the vulnerability, we have to look at the Poisson distribution, the statistical footprint of our laser source. As you can see on the chart, when Jennifer sets her mean intensity, represented by mu, to 0.5, most of her pulses are actually empty, shown here at n equals 0. A good portion contains exactly one photon, which is our safe zone for secure transmission. However, look at the red section of the graph, the multi-photon tail. Even at this low intensity, mathematics dictates that approximately 9% of the pulses will contain 2 or more photons. In the cybersecurity world, we call this the unlocked backdoor. To a quantum eavesdropper, this 9% isn't just noise, it's an opportunity. Eve doesn't need to break the laws of physics or clone a single photon. She just needs to wait for these specific pulses to appear and then take what's being handed to her. This small statistical tail is the singular reason why the standard BB84 protocol, without further modification, cannot be considered fully secure in a real-world deployment.
Now let's look at the actual execution, the anatomy of the PNS attack. As we see in this scenario, Jennifer's hardware accidentally emits a pulse containing 2 identical photons. In a standard setup, John would receive both, and the security would remain intact. But enter Eve, our phantom, in the middle. Eve utilizes a high-transparency beam splitter to tap into the quantum channel. Her objective is simple: split the pulse. She doesn't measure the signal because doing so would collapse the quantum state and alert John. Instead, she siphons off exactly one photon and routes it into quantum memory. The second photon is allowed to pass through to John completely undisturbed. Because John still receives a valid signal, he records a detection event with 0 added noise and 0 signal loss. From his perspective, the channel is perfectly secure. Meanwhile, Eve is sitting on a perfect, unobserved copy of the qubit. She is simply waiting for the right moment to strike. This 3-step process, split, store, and pass, is what makes the PNS attack the ultimate silent threat to traditional BB84 systems.
This is why the PNS attack is so dangerous. It creates what we call the QBER illusion. In a standard intercept and resend attack, Eve's interference would collapse the quantum state, inevitably increasing the quantum bit error rate, or QBER. As you see in the formula at the top, a spike in errors would immediately alert John and Jennifer that their channel was compromised. But look at Eve's strategy here. At time t1, she quietly intercepts a multi-photon pulse. At t2, she doesn't measure it, she simply waits. She only moves to step T3 once Jennifer and John have publicly announced their bases over the classical channel. Finally, at T4, Eve measures her stored photon using that exact basis. Because she now knows the correct measurement to take, she recovers the bit with perfect accuracy and, crucially, 0% added error. From John's perspective, the system remains normal at a baseline 1% error rate. He believes the key is secure, unaware that Eve has silently siphoned off a perfect copy of the data. The security threshold hasn't been breached, but the privacy of the key has been completely hollowed out.
This leads us to the most critical failure point in a quantum transmission: privacy amplification. Under normal circumstances, this is our final safety net. Jennifer and John use this process to distill a secure key, mathematically shortening it to squeeze out any information Eve might have intercepted. However, as you can see on the infographic, the entire process relies on an accurate estimate of how much Eve knows. Because the PNS attack is invisible to the QBER, the system slider remains at a low estimate. The algorithm assumes Eve has almost no information, so it doesn't compress the key enough. The result is catastrophic for security. As shown at the bottom of the funnel, the final key, the one Jennifer and John believe is perfectly secure, actually still contains the duplicate bits Eve successfully stole. While the status light might say secure, the reality is that a duplicate key now exists with the phantom in the middle. The very process designed to ensure privacy has failed because it was fed the wrong data.
So, how do we secure a system that is fundamentally flawed at the hardware level? We introduce the hero of modern quantum networking, Decoy State QKD. As you can see in the transmission line, Jennifer no longer sends a uniform stream of pulses. Instead, she randomly varies the intensity of each one, alternating between 3 distinct types. First, we have the signal state, with our standard mean photon number of 0.5. Next is the vacuum state, which contains 0 photons, a blank pulse used to calibrate the background noise of the channel. Finally, we introduce the decoy state, a much weaker pulse with an intensity of only 0.1. Here is the brilliant part. Because these pulses are identical in every way except for their photon count, Eve has no way of knowing which is which as they fly through the fiber. If she tries to perform a PNS attack, she has to treat every pulse the same way. By adding these decoy pulses, Jennifer and John create a statistical trap. Eve's attempt to siphon photons will now leave a distinct, measurable footprint in the detection rates of the different states. The silent attack is about to get very, very loud.
This is the moment Eve's invisible attack is finally exposed. Welcome to yield analysis, the statistical trap in action. As you can see on the graph, John is monitoring the yields, which is the ratio of pulses sent by Jennifer that actually result in a successful detection. Under normal, non-attack conditions, the ratio of yields between the signal state and the decoy state follows a predictable pattern based on Poisson statistics. However, look at the decoy state column. While the signal state yield looks relatively normal, the observed yield for the decoy state has plummeted to nearly 50% of what was expected. Why does this happen? Because Eve is performing a PNS attack based on photon numbers, she is inadvertently thinning out the weaker decoy pulses much more aggressively than the stronger signal pulses. She has no way to distinguish the two, so her beam splitter siphons from both indiscriminately. This creates a massive statistical skew. John doesn't need to see a high error rate to know he's being watched. He only needs to see this anomaly in the ratios. The thief is caught not by a change in the qubits, but by the undeniable math of the channel. The phantom has finally left a footprint.
To wrap up our deep dive, let's look at the blueprint for a truly resilient quantum network. Building a secure infrastructure requires moving beyond basic protocols and addressing the physical layer of the transmission. As you can see on our final checklist, every AI quantum-secure deployment must verify these 4 critical pillars. First, the source. We acknowledge the use of weak coherent pulses. While they introduce the multi-photon risk, they are the most practical choice for scalable systems when managed correctly. Second, the protocol. Decoy state modulation must be active. This is our primary defense, turning Eve's statistical invisibility against her. Third, the monitoring. We require real-time yield analysis. This is the always-on watchdog that compares expected versus observed detection rates to catch anomalies instantly. Finally, optimization. The mean photon number, or mu, must be precisely tuned to balance secret key rates against the security margin. By integrating these elements, we close the multi-photon loophole that plagued early QKD implementations. Decoy state analysis isn't just a feature, it is the industry standard that transforms a vulnerable laser pulse into a foundation for absolute cryptographic privacy.
If you're building the future of secure communications, you need to know the physics behind the threats. Quantum security is a constantly evolving field, and staying ahead of sophisticated exploits like the PNS attack is the only way to ensure true cryptographic privacy. For more technical deep dives into the world of quantum key distribution, agentic AI, and advanced cybersecurity, make sure to subscribe to AI Quantum Secure. Don't just implement protocols, understand the mechanics that keep them standing. Leave a comment below letting us know which quantum vulnerability or AI security trend we should analyze next. I'm your AI quantum architect. Thank you for watching, and stay secure.